think it's like 10 seconds.
वो तेरे को आएगा, मेरे को तो और
So homework 6, is it working? There's a homework 7 now. That is a support vector machine homework. And after some consideration, I'm going to make it significantly easier for undergraduates. The hard part in homework 7 is implement your own support vector machine. The rest is easy. So undergrad, there's two problems: implement your support vector machine. Both require this SMO algorithm, which is not the best algorithm, but is the one we can use. So undergraduates will not have those two problems. So you still have to run a support vector machine via a library. That's extremely easy. Just set it up and run it. And if you want to implement it, you're very welcome. First, do so. So what are we? Let's put that nice picture here on the board again. That's not it. So find out if that's correct. Ask others. Ask others. What did we do? We said our plan is to separate a bunch of minus points that are on this side and a bunch of plus points that are on this side. And we have a separating plane, wx plus b equals 0. That's going to dictate as a minus side, as a plus side. And we have this margin, which is the distance from the plane to the closest minuses or to the closest pluses. Because the plane is in the middle, will be the same minimum distance to a close plus or a close minus, both sides. That's the plan. And we said for scaling purposes, aka zooming purposes, in order to not depend on where we look at the picture, we're going to establish that these two lines have to be at -1 and +1. These two margin lines, which are given by the data, right? Once I have a plane, where this dotted line goes depends where's the closest minus. Same thing for the closest plus. That's not up to me to decide where is this line. What I'm doing here to decide it's -1 +1, as opposed to say -100 and +100, or -0.5 and +0.5. It's a scaling point, depends where I'm looking at it. How much do I want to zoom this image? So that's called a reference or scaling. So by scale, fixed scale, we get wx plus b equal smaller than or equal to -1 if y is -1, and wx plus b it's at least +1 if the label is +1. That's what we said, okay? And then we did some arithmetics in here, and we've got this row. I won't repeat the mathematics. It's 1/2 of x1 minus x2, and then we've got w is parallel as a vector with x1 minus x2, which implies w times x1 minus x2 distance is the same as w times x1 minus x2, which further implies this row is 1 over. Now, the w scale, fixed scale, how do we fix scale? By scaling w and b. That's how we affect the scale. We can't change the data points. So we can multiply the w and b with some values. The plane will stay the same. But then we can obtain these -1 and +1s margins. So now we're looking at this distance. That's the minimum distance that we care about. And we say, okay, we scale w. The only thing with w is to find the right w now in terms of rotations. Where is the correct separation in terms of, I can rotate the plane up and down, back and forth. So the SVM primal problem is we want to maximize margin that is minimize the W norm. We're going to do the square one for to make it easy math. And then subject to constraints. I wrote both into one piece, right? Because I can write both of them. If I multiply with y, both of them become y times wx plus b is bigger than +1. For the positive side, if I multiply with +1, it stays the same. For the negative side, if I multiply with -1, I get y times wx plus b greater or equal than +1. Right? So I can write them all in this form. This is a constraint problem because I have these constraints. This is one per data point, right? For each data point, theoretically at least, I have a constraint right there. And the constraint says we want the minuses to be at this line or farther, and we want the pluses to be at this line or farther. That's what constraints are. So now we said we have this new technique from last time, which is the Lagrangian multipliers, that says, how do you solve these problems? This guy Lagrange figured out that the objective function, which is this, the solution for this whole problem is when the objective is tangent to the constraint problem. We showed this last time, right? So then, because they're tangent, we have a factor between the two tangents. That's the Lagrangian multiplier, and it's 1 per constraint. So I have 1 Lagrangian multiplier per constraint. So alpha I is the Lagrangian multiplier for constraint on xi, and then the Lagrangian is a function the W B's and B is only one B and alpha. It's 1/2 squared on minus the sum from I equal 1 to n alpha I y I plus B is 1. That is my Lagrangian function. And we are looking for the minimum. So just like we've seen in the example last time, what we have to do here is take derivatives, right? Derivatives with respect to what? W and B and alpha. So let's do so. If I differentiate the Lagrangian with respect to W, it's a vector derivative. What do I get? We do that trick with, I can apply the derivatives like I learned them from multidimensional W's to the multidimensional W's. We had this discussion at regression, remember, when I did it nice and easy the first time, and then we went over and say, hey, how do you actually do matrix derivatives here? You need a trace operator, you need all kinds of other things. But let's just assume that stuff works. So if I take the derivative, the mechanical derivative with respect to W, what do I get? From the first term. W minus the second term. The sum will remain a sum. And then B is not in there because B doesn't affect W. So who is affecting W? Alpha I, yi, like this. There's x2. Okay. So that has to be 0. So that implies I've got a relationship now that says W has to be sum over I equal 1 to n alpha I. Got that. Okay. How about take the derivative with respect to B? What do I get? The first thing is 0, right? There's still no B here. How about the rest? What happens to this B in here? Minus sum from I equal 1 to n alpha I has to be 0. So then this sum has to be 0. Okay? The differentials with respect to alpha in the Lagrangians are trivial differentials. They will immediately give me the constraint back. Right? That's what they do. So the Lagrangian works in saying some Lagrangian multipliers would be non-zero and some Lagrangian multipliers would be 0. We'll see that in a second. Now, how about this one here? Can somebody describe this equation in English? So this is saying there are a bunch of coefficients alphas, right, associated with each data point. Let's try to split this equation into positive points and negative points, right? So how does this look? Sum of all I equal 1 to n with the condition yi is plus 1. That's the positive point. So for those, what do I get? Alpha I. Right? And then I get a plus sum from all data points with yi equal negative. That will be who? Minus alpha I. Let's call this j's to be more clear. Then I get 0. So that if I am to rewrite this, I get sum for all yi is plus 1 of alpha I. I move the other one on the other side. It's sum from all yj equal minus 1 of alpha j. So this is saying these coefficients on the plus side, the sum of the coefficients on the plus side has to be equal to the sum of the coefficients on the minus side. So we like to think of these alphas as forces to the plane. How much a point pushes the plane. If you think of this plane as being some sort of equilibrium between the plus and the minus points, every point pushes a little bit because every point wants the plane far from it. This point here doesn't push that much because the plane is already very far, right? So the force that this guy has on the plane, it's alpha, it's not too much because the point is already far away from the plane. But this point here, if I have a point in here, which is not allowed by definition of our margin, that will be a large alpha because it pushes the plane hard. And if those points will have magnets in them, obviously the ones close to and the plane will be made of metal, then every point close to the plane will push the plane much more than a point far away from the plane. Think about all these points are being magnets pushing the plane out. Same thing will happen here. This will have a reasonable force, this will have no force, and this will have a huge force. So what this theorem is saying here, or differential, is saying the forces on the plus side is equal to the forces on the minus side, which makes sense, I think, because we know the plane has to it's been an equilibrium position as far as pushing goes, right? We said from the beginning we're on the plane that's in the middle. That means it's equally pushed from the plus side and from the minus side. So that equation here confirms that thing. Okay, so now we're going to take a short break from this. To this, yes?
Can I ask a question about fixing scale?
Yes.
So in this case, we have fixed the scale to 1, right? So can we fix it to any number, to 10 or?
Yeah, just multiply everything by 10.
Multiply everything? You mean data points?
No,
By 10?
I mean W and B.
When you multiply by 10, what happens to the surface?
The surface is the same.
Uh-huh.
All the points that were positive remain positive, points that are negative, negative, except this margin, instead of being minus 1, is now minus 10. Because I multiply both W and B with minus 10.
Huh.
And this would be plus 10. But it's just a reference point. You want to set it up plus 10. It won't change the math at all.
But what's the point of fixing scale?
If we don't fix the scale, there's an obvious way to minimize this. Just drive W down,
Huh.
way down, right?
Huh.
That is, move away from the picture. We want to fix a reference point before we start minimizing W, otherwise there's a trivial way to minimize W. But we're not interested in that way of minimizing W because that doesn't change where the plane is. We're interested in once we fix a scaled reference point, rotating the W to see what's the best W as far as margin goes, right? Our plan is to rotate this W here to play with, to figure out what's the best way to get large rows, which is the distance we care about.
But we're also assuming here that there's no data point in between.
For now, we said there's no data point in between.
Uh-huh.
The minimum or maximum you can go, the closest you can go to this plane is here, which if the data is separable, is true. If there is a separation plane that leaves all the minuses here, all the pluses here, setting this to minus 1 is purely a scaling zooming point. But if there is no separability in the data, right? Like then obviously we can conceive a data set that has pluses and minuses intercalated, we can separate them. Then we're going to have to allow some errors that go on the other side. Because a linear function will never be able to separate everything. In practice, even if it's separable, we want to allow things going in and out for flexibility. Right. We'll get to that in a second. Yes?
So, like, if you were to think about this entire algorithm in English, would that just be like maximizing the confidence of the points most closest to the boundary?
Correct. It's saying points are fixed, so we can't change the points. We change the W. So what you're saying is, we want to ask what's the best W, which is plane, such that these closest points to the plane have largest possible confidence. In that sense, it's similar to what active learning is trying to do, right? This active learning, once you decide, okay, label a few points, is going to reposition the surface, plane or tree or whatever I have, in such a way that the closest points to it are not, you know, are not close anymore, if that's possible. So if you notice in active learning, I have a line and I pick a point close to it and I label it, that's going to move the line. Okay, so the quick 5 minutes break I want to make here is to discuss saddles. You ever been to ever been a horse, somebody riding a horse? They use a saddle most of the time, right? So how those saddles look like? Something like that, right? That you can put on a horse. So I would like to draw a saddle. I'm not good at it. You can try too. You know. So how's a saddle looking like? If the horse is like on the board, this goes over the horse, right? And that's over the horse. That's the other side of the saddle. And over the horse, the saddle is this way, right? And try to do my best here. Right? It goes like this. That's the horse is right under. Right? But what about from the top? How the saddle looks from the top? If you were to cut the saddle like this, you're going to see exactly this thing that goes over the horse. But what if I'm to cut a slide like this? What am I going to see? It's going to look like this. Right? And we have to imagine now, we can get some pictures. At the end of the lecture, we're going to get some picture about this. Again, if the horse is like that, head and tail, over the horse, the saddle is this way. But for a person to sit in the saddle, I'm in the saddle now, how is the saddle going to look from my point of view? It's going to be this way, right? So I'm sitting on a saddle that's this way. Let's call it convex. It's like it holds water. But what about over the horse? The other is concave, right? Anti-convex. So we got to spend some time understanding exactly how this saddle looks like. It's in one way, it looks this way if you look from one section. But from the other section, if you look this way, the saddle is like that, right? Because a person sits on it, so it has to be this way, but over the horse is that way. So, why I like the saddle so much? Everywhere I cut the saddle alongside, I'm gonna get this convex section of it. The convex section has a minimum somewhere. Right? Each convex section has a minimum. Maybe that's the minimum, that's the minimum, that's the minimum, so on and so forth. And I'm interested in the maximum of these minimums. So I'm cutting the saddle this way. Every time I chop it off, I see a line that's convex. And for each line, I have a minimum. Which line has the maximum minimum? The one in the center, the one at the very top. This line at the very top here, before it starts going down, this line, if I take the minimum of this one, that's the maximum minimum you can go. Any other long cut will have a minimum that's lower than this minimum. So what did we do here? We took the saddle that was horse stays this way, chop it off along the long side of the saddle. Everywhere you chop it off, you get a convex curve, and then that has the obvious minimum. And then the curve that has the highest minimum is the one at the top of the saddle. That's that minimum in the middle of the saddle is the maximum of all those minimums obtained out. So there is a magic point here, which is the maximum of the minimum of long cuts. Right? If I take the long cuts, which are convex, each one of them I take the minimum point. This point here is the maximum of those. Now let's do it the other way. Instead of cutting the horse along the horse, I'm going to cut the saddle, sorry, perpendicular to the horse. If I cut the saddle this way, what am I going to see? I see not a convex, right? Again, I chop the saddle this way, the saddle stays over the horse, so I'm going to see a line like this. I'm going to see one of these things, right? This one has what? The maximum right here. How about this one? The maximum right here. How about this one? Anywhere I cut it, I get a maximum, right? The maximum will be probably on that middle long cut. So what if I want the minimum of this maximum? I say this point, the same point, is the minimum of this maximum. Right? So this is the minimum of the maximum of the shortcuts. That is perpendicular to the horse. It's an extremely important mathematical phenomenon discovered in 1950s or so, very recent for this kind of math. Because this kind of math does not involve new developments like topology, you know. It is still based on linear algebra and differentials that were known for 200 years. But this phenomena was not clarified by before 1950 or 1960s, not too long ago, by people who are now famous and who said there is this saddle property that Lagrangian functions have in certain conditions. And that the theorem is that if you take the maximum along the minimum of the long cuts, it's the same point as the minimum of the maximum of the horse cuts. That's called the saddle point. So in this theory, the saddle point would be that point which is maximum of the minimums this way, or the minimum of the maximums the other way. Same point. So this is the saddle. That has important implications to what we do here. It means that looking at the problem for minimizing certain value along this way, it's the same problem as maximizing some value along the other way. That creates this duality that we're going to talk about now. So we're going to take this primal SVM problem, which comes directly from the geometry. Because the way we formulated this in here, we specifically say, I want this to be maximum. This meaning 1 over the W, so I got this problem. Now I'm going to formulate the same thing in terms of a dual notion, which corresponds to this saddle duality. Instead of minimum along this way, I'm going to ask for maximum along the other way. And the people who did this, Karush-Kuhn-Tucker theorem. That's a theory of mathematics that governs how this transformation between the primality and duality with the saddle point goes. There's 5 conditions in there to be satisfied, and they of course will be satisfied for our case, support vector machine Lagrangian. So let's do so. How do we get the dual problem? Very easy. We just look at this stuff and replace this in our Lagrangian formulation. So we're going to say, well, let's take this Lagrangian and we're gonna replace, I guess, W with this stuff in there. Let me write it one more time here before I do the replacements. So what I did here, I just play with the arithmetics like this. I wrote it as W transpose times W. Then I open the parentheses, alpha I W Y X is in here, alpha I W Y B is in here, minus 1 times alpha I times minus it's plus sum of the alpha i's. So now let's replace W. What are we going to get in there? 1/2 this is in one shot. Let's see if we can follow it. So alpha I y I b is alpha I y I b. Sum of alpha i's is sum of alpha i's. In here, when I plug in the W, so this would be 1/2 W transpose W. That's 1/2. W is sum of alpha I yi xi, and then again, so let's transpose, and then sum of alpha I yi, let's call it j this time, alpha j yj xj. So what happens when I do this multiplication, everybody gets multiplied with everybody. I get all the pairs ij, and I get all alpha I, alpha j times yj xi xj. Yes?
Is there any reason you changed the subscript to J?
Right, because the summation is from I equal 1 to n, and then in here it's also 1 to n. I use different indices so that when I do the product, I'm not confusing i's with j's.
Oh.
I mean, I wouldn't be able to say there's a pair, right? There's alpha 1 that gets multiplied with alpha 1, that's alpha I, but then there's alpha 1 multiplied with alpha 3.
Oh.
Right? So I need to be able to put my hands on all pairs. If I write this in terms of I and this in terms of I can't do the pairs. How about this one, which is the same, where this one came from? It's the same except for 1/2. This must be coming from here, right? So I have a sum of alpha I. What do I have? I have sum over I of alpha I, yi, xi, wt transpose, right? This guy here. I mean, I can't reverse them, that would be incorrect. It has to be wt transpose xi for the multiplication to work. So what happened in there? I substitute w with my formula, right? So this would be the sum for I of alpha I, yi. Now w is a sum in itself over j equal 1 to n alpha j x j y j times xi. So what happens if I open this parenthesis again? I have this term here, but I replace w with the sum of alpha j y j j. I get again multiplied all pairs of alphas, y's, and x's. Ends up with me. Okay, well, let's take it slow. Let's see what happens. I started with this Lagrangian. I took derivatives. Out of these derivatives, I got those two equations. So now what I'm doing, I'm plugging the w back into the Lagrangian. That will get rid of w's because I'm only going to be left with alphas, y's, and x's in there, right? And that's going to be the dual problem. I won't have a w or b. I'll only have alphas and x's and y's. Notice that in here, I didn't have alphas in the original primal problem, right? This problem says, give me the w and b that satisfy these constraints and maximize or minimize the w norm. Now, I'm going to specifically write the problem in terms of alphas, which are these Lagrangian multipliers. I'm saying, I want to characterize this optimization not in terms of w and b, but in terms of alphas. Because if I have alphas, I can compute the w. So the optimization in terms of alphas is the dual problem, is the one under the saddle. The primal optimization is the one over the saddle. But both of them will end up with a solution in the saddle point. So, okay, how do I plug in w back in here? I'm going to have to say there are two places. So I first open up this parenthesis, then I plug in w here, and I'm getting this term. And then I plug w in here, and I multiply with all the alphas, y, and xi. W itself being an alpha, sum of alphas, y's, and x's. And I get again all the pairs. This one has a w from the beginning. The other one does not. So how about this?
That's 0.
That's a 0 because if you take the b apart, I have that equation that says alpha, sum of alpha I, y is 0. So this will come up to 1/2 sum over minus 1/2, I believe. Because it's half minus a full. I'm going to group the terms like it's written here. Y, I, y, j. Right? So this is kind of the coefficients. This is kind of the product of the labels. And this I can write as the dot product between xi and xj. That's exactly this quantity. So minus half of that plus the sum of alpha I. So let's write this optimization problem now, which is the SVM dual problem. This problem is in terms of alphas. The primal problem was in terms of w's and b. So this problem says maximize this value right there. Subject to, it has to be constrained. What are the conditions? So this condition will happen here because that's how we obtain the dual. We plug in the W in the formulation. So this is our bridge, so to speak, between the primal and the dual, the relationship between W and alphas as function of data points. So that's going to happen. We don't have to worry about it. But this one is a constraint we have to enforce here. Sum of alpha I, yi equals 0. And there's another constraint.
Summation of alpha on the left hand side and the right hand side on the right.
That's this one. This is exactly saying if you move the alphas on the negative side on that way, the sum of the first side is the sum of the other side. What's another constraint that needs to happen here? This is a little bit hidden right now, and it's an exercise in the homework that will force you to read these Karush-Tucker conditions. For this whole thing to work, there are 5 conditions, which all 5 happen to work in our case. You don't have to worry about support vector machines not satisfying the KKT conditions because they always do. One of these conditions is that the alpha i's have to be positive for all I. This force that we're talking about pushing into the plane, they can't be negative. We're not allowing points in here to drag the plane with them. If they're far away from the plane, good. But they can't start pulling the plane out and say, I want to be closer. That would be a negative force, right? All forces have to push into the plane. So this is a dual problem. That's the one that everybody, including us, is going to try to solve. How do we solve this? I mean, if we take again the derivative Lagrangian, we get back to the primal problem. So how do we solve it? We need some sort of technique to solve this problem. Repeat, what are the given stuff in here? X and Y are given, those are the data points and the labels. And what are we trying to find? The alphas. Alphas are real values, right? Positive. 1 per data point. So how do we do that? There is another, I'm willing to take any crazy ideas. How do we solve this problem? What kind of system or what kind of function is this in terms of alphas? Is it a linear function in terms of alpha?
It looks like a line passing to 0.
This stuff is linear, right? But this is not. What kind of term is this? It's a quadratic term that involves 2 variables in there. So what people use in here, mathematicians, is what's called a quadratic solver. A quadratic solver takes an objective that is formulated in terms of variables, and variables multiply with themselves. That's quadratic term. So in other words, if I allow x1 to be multiplied with x2 in my objective, that's a quadratic term. If I allow to multiply again with say x4, this is now a cubic equation. So this is not cubic, but it's quadratic. So the quadratic solver has to take the variables, has to take the coefficients, which are all given by xi and x's and y's, the labels and the points, and has to give me back the alphas. That is the solution to this maximization problem. So there's some very efficient quadratic solvers. Some of them even make money as a plug-in to MATLAB, for example. MATLAB has a generic quadratic solver, but it's not that efficient. So most of the people who work in support vector machines have digged up really good the quadratic solvers. So a support vector machine library would either implement a quadratic solver or rely on a quadratic solver to solve that maximization problem. Again, fit a bunch of x's, a bunch of y's, ask for the alphas that satisfy these conditions, of course, and give me the maximum function, which is the maximum of a quadratic function. It's a quadratic function of many variables. It's not really simply a alpha squared plus b alpha plus c. maximize that quadratic function, because it's not just one alpha, there are many alphas, right? How many alphas? And so if I have spam base, that would be 4,000 alphas. If I have and these digits, that would be 60 or 70,000 alphas, right? Before I move on, there is another important KKT condition. Question?
Is it not possible to solve the primal problem, or is it too hard because the alphas vary?
To solve this problem directly. Yeah, I think that's much harder. As far as I'm aware, everybody solves that problem.
So you said that in the dual problem, all of the alphas are the number of samples, right?
Each alpha corresponds to a data
Corresponds to a
point.
sample. And what we are trying to find is, so if we put it in a quadratic solver, it will give us the values of the alphas.
Yeah.
So what we are trying to find overall is which sample is closest to the given samples.
We're gonna end up finding that, but our general purpose is to maximize this objective.
Yeah, but maximizing that objective will give you some value of alpha which corresponds to some sample, right?
It'll give me values for all alphas, not
Yeah.
just for one alpha.
Yeah, for all the alphas, but those alphas would be corresponding to the x and y's that we have given it.
Right.
So for each x and y in our data set, we will find a sample or some representation that is most closest to that particular sample.
The alpha for each sample, it's only one value, so it's not a representation for the data point.
So so it's just a scalar value.
It's just a scalar that indicates the force this point pushes into the plane. So you can use that alpha to say how close this point is. The ones that have a strong alpha are the ones closest to the plane. The ones that have a weak alpha are the ones far away. That's true. But in terms of a representation, I'm not sure, because each alpha is one real value.
Can we say that the ultimate goal of calculating all alphas is to identify the exact position or the location of the line?
Plane.
The separation plane.
Yes.
Is it so?
Yes. Because the primal and dual are equivalent problems. Solving this problem,
Uh-huh.
the KKT theorem says it's the same as solving this problem. The solution that you get is exactly here, which is the exact solution for this problem. So then the one that maximizes the margin, puts the plane in the middle, is the one that maximizes this alpha objective here. I want to make an important observation here that's going to be important for next time, just to clarify, because we all have been looking at these monsters. It's an absolute lucky thing for us machine learning people that all the math comes down to a forming here where the x's come in pairs. So look at this objective. Of course, it has the alphas variables. Y times yj is a product I can make very easily. It's either +1 times +1 or +1 times -1 or something like this. But the xi and xj, all the terms in here will correspond to a dot product, xi times xj. In other words, there are no loose xi's or xj's in this objective. There's no plus alpha 2, x2, something like that. All x's that you see here are a dot product with another x. This is a very important observation for machine learning purposes. And we'll see this next time, in that it allows us to do non-linear separation. This particular issue, the fact that in that objective all the x's come in pairs, gave somebody 30 years ago an idea to say, how do I change that a little bit to allow it here, this plane, to actually not be a plane, to be something like round. And that became a machine learning technique, not just for support vector machines, but for many algorithms. So that's what we're going to do next time. But for now, let's worry about those alphas, right? Before I move on, there is a KKT condition that's important to us. That says, for each I, alpha I times the constraint this constraint. Yi, so this is the force, and this is the constraint, was yi wx plus b minus 1. This is 0. Which means two things. Either alpha I is 0 or the constraint is 0. Yi times wx plus b equal 1. We don't have the time and the space and the scope to prove the KKT theorem. It's way too complicated for us. So that's the kind of thing that mathematicians in the room will go home and say, I want to waste my weekend with KKT. Go ahead. Fine. So it's a very important theorem in linear algebra for Lagrangians. And the result is critical for us for the support vector machines. What does it say? Either the points don't matter, right? Or they are where?
On the margin.
On the margins. This is saying, in plain words, the points that matter for this hyperplane to detect the hyperplane are the points that are on the margins, because the point outside the margins have the force equals 0. You can throw them away, nothing has changed. So that's good, right? Because it means, at least intuitively, even if my data set has 60,000 images, I won't have 60,000 of points that matter for my plane. It's not like I can select them in the beginning, which ones are those. I have to figure them out. But still, I can expect that most of them will have a force of 0, so they won't affect the classification rule, aka the plane. Does that make sense? So, in reality, like I said, we're going to have some points inside. Those will obviously also matter. They will have a positive force. But at least the ones outside the margins have 0 alphas. So the theory of support vector machines is very nice that way. It says the whole problem reduces to the few points that are pinpointing this plane. You know, some minus, maybe the ones inside, those ones at the edges, and everything else you can throw away. Doesn't matter for SVM. If I can somehow know this in advance, which ones to throw away, that would simplify my life a lot, including the quadratic solver. Because in this quadratic solver, if I throw in 60,000 alphas, it's a much harder problem than if I throw in 6,000 alphas. Right? The quadratic solver will take time proportional with the number of pairs I have. So if there's 60,000 of them, that will be a huge running time. That's why we don't implement a quadratic solver. But you'll see when you run the support vector machines with a very mature library, which is quite a few of them that people use, it will run decently fast. It's not like it's going to take forever. Yes?
What will happen if a negative point is on the positive side of the line?
That will be the same like this one. If a negative point is here, its margin, it's way negative, right? And it's not like we can ignore that point. It's in the wrong side. So we'll have to deal somehow with points both inside the margin but on the correct side and on the other side completely. Right? So we're going to call these outliers and we have to see what can we do about it.
So SVM only is concerned about the data points which are exactly on the margin. So doesn't it mean that SVM doesn't make use of the amount of the data they have in hand?
It does, because, I mean, it does by throwing it out. It doesn't throw the data out in advance.
Yes.
It has to look at it first to determine which points are close to the plane. Those are the ones that matter, and which are the other points which do not matter. So it's not like you can make this selection before you run the algorithm.
Yes.
But in the algorithm, inside somewhere, is determined which points are the ones that matter. And these points, I think I said already, are called support vectors. That's where the name comes, support vector machines.
Professor, what's the point of throwing these data points away after we train it? What's the point of
We're
that?
not really throwing it away. All I'm saying is, as a result of training, they came out as irrelevant. So whether we use them or not, it wouldn't make a difference for determining the plane. So we don't want to throw them out. It's just we feed everything in, and as part of the procedure here, we're gonna get this is the super vector, and this is irrelevant. So this is going to be determined by the algorithm. Which points are the one that matters? The support vectors. Matters because the force of pushing to the plane is positive. And which points do not matter? Because the force is zero. Yes.
So for that, can we just negate that point and negate the label as well, like we did for percent now? The outlier.
This one,
Yeah.
if we negate the label and negate the point, we still an outlier on the other side, no?
If we just negate the x, then
I mean, if we put it here and then we negate the label, we get the
label.
plus one.
we don't negate the label. Just negate the point.
But that doesn't work, right? I mean, how can you go like that with a paintbrush and? Okay, more questions? Yes.
Professor, I'm trying to understand the equation below the A1 is 0, Y1, blah, blah. So does it means that alpha I is bigger than 0? Like, does that say meaning?
Right, because this equation has to be zero.
Uh-huh.
Either alpha I is zero,
Uh-huh.
and then that's not a useful point.
Okay.
It's outside the margin. Or the constraint is satisfied with equality, which means the point is right on the border,
Uh-huh.
and that's called a support vector. That's a point that supports the plane.
So the equation in the left side, like y1 wx plus b equals to 1, is it the same thing as saying all alpha i's will be bigger than 0?
Yeah, it's saying, geometrically it's saying the point is here or here, it's on these lines. And that means these are the points that are supporting the plane, aka they're holding the plane in the position that it is.
How about the 1 value? Like, does it mean that margin should be exactly 1?
This row,
Uh-huh.
the margin is actually this, right?
Uh-huh.
So the whole theory here says this is being maximized.
Yes.
So the maximum value that you can get for rho, it's both in here, right? Because minimizing directly norm of W, or maximizing this one here, they will give you the maximum rho distance. So they will maximize this distance between the plane and the margin line. Okay? Now this duality appears in many problems, not just in here. This is not the only optimization problem that passes through KKT conditions and obtains a dual and so on and so forth. You can do this with many functions, including regression. So we can do this with regression and obtain a dual regression. Duality, you can view it in two ways. Either in terms of the variables. A duality refers here to WB is the primary variables and alphas are the dual variables. Or we can see it in terms of dependency of the data. The primal depends on each x and y. The dual depends on the pairs of x's and y's. Because if you look at this expression, we don't actually ever saw an x or a y by itself. All we see is pairs of x and y's. This is an important thing in machine learning. That's a much more general theorem that says every machine learning algorithm that works with data, x and y, can be written to work with pairs. So for pairs, what I get is not something about the points. For pairs, what I usually work with is how similar the objects are. So when you think of pairs of objects, whether they're patients or emails or images, this here, it's how similar is that image with the other image, or that email with the other email, or the patient with the other patient. So again, in machine learning, everything that we can do directly based on, say, patients, we can somehow morph it toward not to direct value of the patients, but rather how similar two patients are. There's a theorem that has been shown that if you can detect similarity between your objects, it's as good as any machine learning algorithm having a good similarity function. If you can tell if two images or two emails are, how similar they are, and if that function works well, that's equivalent to solving any machine learning problem. Like with recommendation systems, if you can tell what movies are like what movies, you can immediately recommend the right movies to the customers. All right, so that's a plan. So anybody figured out what I can do if I'm not smart enough to apply a quadratic solver? So we don't do quadratic solvers here, that's purely in the math department. We're gonna take a library, pass alphas to it, see what comes out, like pass the whole system to it. The quadratic solver supposedly is gonna determine some alphas, right? Suppose I'm not that smart to write one, but I wanna write some algorithm, what do I do? Like in EM. In EM we couldn't, this is not EM at all, but in EM we couldn't optimize for all parameters at the same time. So what did we do? Fix a bunch of them, right? And then optimize for the remaining ones. And then fix those so that we just optimize and optimize the other ones. So how they're working here?
Fix one, then fix one alpha, and then optimize for the other.
The other would be 59,999, right?
No, I meant one iteration, fix that. So we have I, j.
So can I fix all alphas except one and optimize that one and do that coordinate ascent sort of thing, right? One by one optimize. That's coordinate ascent, right? Instead of trying to optimize all parameters, fix n minus one of them and optimize the last one, which is a simple linear function, and then move on to the next one. And you hope by coordinate, one by one optimizations, eventually you optimize all of them round robin sort of thing, right? Are we familiar with that? AM was a little bit smarter than that. I was saying, let's chop them into two categories, the E part and the M part, and then optimize the memberships in the E step. That was the ZI case. And once we fix those, optimize the parameters mu, sigmas, and pi's on the other hand. I'm asking in here, can I fix all of them except one and optimize that one? In other words, pick one of them, alpha 3, fix the all other alphas, alpha 1, 2, 4, 5, 6, so on and so forth, and just say, okay, work on alpha 3 to improve this objective. Make sure it's positive, just update the alpha 3.
So if you change only single one, the first condition would be.
The what?
If you change a single one, the first condition would be.
Right. That's what you were about to say. Right. I can't do this with one alpha because this, assuming currently I have a valid set of alphas, this linear form here, it will not allow me to change one alpha. Right. Everything fixed, it will force the last alpha to also be fixed. Right. Just think about it. It's a bunch of numbers added up goes to 0. I can't just take one of them and change it because that means they won't sum to 0 anymore. So I can't do one variable with the other n minus 1 fixed. What else can I do?
Can you do one positive labeled data point and one negative labeled data point? And then if you increased one, you decrease the others alpha.
With the same amount.
Yeah.
So I could try that. I can pick one positive, one negative. And because of this condition, if I increase the positive by 0.5, I have to decrease the negative by 0.5 to make sure it sums up still to 0. But I think this idea is not restricted to a positive and negative. I can pick any two alphas And due to this condition, I know there's some more difference. It's a fixed amount. And as long as I keep that fixed amount in there to satisfy this condition, I can play with, say, okay, give more to this guy or to that guy within that sum to see what increases my objective here. Hands up, who's with me? So what did I do? I can't pick one and change it, keep the other ones fixed, but I can pick two of them and within a fixed sum or difference to satisfy this equation, try to play with them to see if that's going to increase my function. Shouldn't be hard, right? But think about it. If I only pick two of them, so suppose I say change alpha 1, alpha 2, but the rest fixed. I'm going to have a condition that's alpha 1 plus alpha 2 equal some value. That's constraint. Right? Either the sum or the difference, depending the sign of y's. And how is this maximization in terms of alpha 1 and alpha 2, how is it going to look? I want to maximize. If I ignore all the other variables because the other alphas are fixed here, they're not changing. Only alpha 1 and alpha 2s are changing. How would this look, what I'm trying to maximize in alpha 1 and alpha 2? Alpha 1 plus alpha 2 minus 1/2 alpha 1, alpha 2, x1, x2, y1, y2. That's the term with both alpha 1, alpha 2. That's a quadratic term. Minus there is a alpha 1 times something, right? There is entire terms that contain alpha 1 and no alpha 2. Those will be constants because they don't change. So that's going to be a sum from I equal 3 further to what? Alpha I x1, xi, y1, yi, and then I have minus alpha 2, another, so that's constant here. So I get a quadratic term that says I want to maximize alpha 1 plus alpha 2 minus the quadratic term, minus alpha 1 times something, minus alpha 2 times something, is really alpha 1 times the coefficient plus alpha 2 times the coefficient plus alpha 1, alpha 2 times the coefficient. So that's a simple quadratic equation with two variables that I need to figure out within this constraint. So I can't move away from this constraint. Within this constraint, what change do I make in alpha 1, alpha 2 to get the maximum value? A step further, what people will do will replace alpha 2 with value minus alpha 1, plug it in here, and then that's a quadratic equation alpha 1, solve that equation, and whatever the solution is, that's the update rule for this iteration. Then at next iteration, I can pick two different alphas. I can pick alpha 4 and alpha 7 if I want to play with them. This algorithm is called the SMO algorithm. So it's two alphas at a time. I can't pick one because that's nailed down, so I'll pick two at a time and update them.
How long do you keep doing this?
For a long time. Quadratic solver will be much faster.
And how do you pick two at random?
The last 10 pages of notes are about how to pick the two alpha and alpha J.
Are the alphas can they be repeated?
Of course they will be, because it's an iterative procedure, coordinate ascent. So you do something, change, then you move to another pair, another pair, another pair. However, at some point, some alphas will become clear. Those are the zero alphas, right? They are the ones that don't matter, so maybe we can just set them to 0 and move on.
What if certain alphas are 0 plus and they had y ws plus p equals 1 in the KKT equation?
That's okay. That if alpha is 0, we don't need to worry about that point. Right? As long as we know alpha is 0, ignore it, and then it doesn't matter.
What exactly does coordinate ascent?
Update one by one. Instead of update all of them at once, gradient descent update all the variable at once. Coordinate ascent, update by coordinate. Fix the other ones, change one.
How do you know that we are at the solution now? See, we did it for like a million times.
Well, as long as this doesn't increase anymore,
Okay.
the objective does not increase. Whatever alpha and alpha j we pick, we can't increase the objective. We say probably we're at the end, even if we're not sometimes. Okay, well, we need to deal, we can't really do SVM because in practice, we can't go for separable data. We have to include those error variables, okay? So that, it's one thing. The other thing is, how many things are we expecting to be zero? Again, a shortcut in this kind of algorithms is often to say, if I predict something will be zero, right, I can drop it off and not worry about that alpha anymore. So the more things I can drop to zero, the faster it's gonna go. There's something in my mind that I missed here about the Harush-Kontaka theorem, but that's okay. We can move on. So what I want to do then is introduce those error variables. Oh no, what I wanted to say is suppose all this is well and done, figured it out. How do I make predictions? So I have the training done, which means I have the alphas, which means I have the W. And probably it's not yet clear how to find the B, right? I mean, W is a formula of the alpha, y, and x's, but who's B? How do I get B? Assuming that I run this algorithm, either a quadratic solver or an SMO, I have the alphas in my hand. Immediately I can get W. But I need a B, right?
Can't you get from that? You know all the other values. I had a column x1 in the beginning.
So B comes from here and from here. The closest points must be at the margin. So how do I get the B? I have to solve for which ones are the closest points once my optimization is done? Huh?
To solve for the support vector.
For the support vectors, which are the ones with non-zero alphas. So support vector xi has alpha I positive. And if yi is -1, I need wxi plus b has to be smaller than -1. In fact, when alpha is positive, this will be about -1. That means b, this is smaller or equal than, b will be smaller than -1 minus wxi. And if yi is +1, wxi plus b has to be bigger than +1. That means b has to be bigger than 1 minus wxi. So what people do in practice, they take all the support vectors, they compute a minimum b to compensate. So this would be b mean is the minimum over all data points that have yi equal -1 of -1 minus wxi. And b max is the maximum over all data points that have the y positive 1 minus WXI. And they take this minimum B I need and the maximum B I need to compensate, and then take some sort of average between those two values. So the B has to be an average point between those. Ideally, it would be the same B for everybody, but that doesn't happen, so I take an average or of the extremes.
They would be the same if it is linearly separable with margin.
Right. If the points that have alpha positive exactly on the margin and nothing else, it would be the same B, one value. But in reality, it's not.
If the thing's further away, you're saying if nothing is closer than the margin to the separating point?
Nothing is closer to the margin if the data is separable, and I'm now willing to make exceptions, so to speak. The problem with even the separable data, there is a picture I want to show you later down here, is that instead of creating a line that separates everything perfectly, but it's very, very close to some points, it's much easier to declare one of those points an outlier because it looks like out of the pack, and then I get a line with much bigger margins to the rest of the data. We'll see that picture as soon as I connect my projector. So even a separable case, it may be easier to allow some errors to have large margin, thinking some of these points are atypical, if not deadly wrong, rather than trying to go exact on everything.
Till now, have we done anything that allows us to have points inside the margin?
No. So let's do that now. I'm going to allow the point in here to be inside. So this is the inside margin. That means error. But I'm not going to use the word error. I'm going to call it slack. So this letter zeta I, slack variable for the data point psi. The primal. So this is how much I want to allow a data point to go inside my margin. I want to minimize So instead of saying my point x has to be, remember the original constraint, the pluses have to be a +1 or further, the minuses have to be a -1 or lower. Instead saying, well, it doesn't have to be a +1. We can allow it a little bit inside the margin because it's 1 minus the zeta. Zeta dictates how much slack it has, right? So zeta would be the distance from here to here. Because this is how much it got in, right? How about this point here? If this is a minus, what is its slack? How far this point got in?
Negative.
Yeah, but from where do I measure the slack? From what margin? This or this?
Negative margin.
From the negative margin. The slack of this guy has to be this. Right? Because he is a negative, supposed to be here or farther, but he got all the way to there. So with those slack variables, I can say, okay, how about this point? What is this slack? It's from the positive margin to here. Right? So can I allow a lot of slack in here? Effectively, everybody can go wherever they want, no problem. I have to include a penalization in the main objective, just like regularization. I say the more slack you allow for some points, for a lot of points, the more your objective is useless. Because then, of course, if every point can be whatever with no penalty, then is no constraint for my plane to do nothing, right? It's like I say, put whatever points you want in any position, so okay, any plane will do that. So then I have to pay somehow for allowing the slack. So I have this here in the objective to control how much total slack I allow, and a parameter, hyperparameter C, just like regularization, how much this term matters in relation to this term, right? A large C, an infinite C, will effectively do what? Not allow any slack, right? If this C is infinite, anything that's not zero, perfect zero for slacks, will make this objective impossible. And if C is very small, 0.00000 means I'm allowing a lot of slack, so then anything goes. So this is something that needs to be tuned, just like a regularization hyperparameter. Well, if I do this, what's the dual? I won't take the derivatives again. You'll be surprised how little this whole slack variable changed the problem. How is this different from the original dual? Where is the dual here? It's in here, right? What has changed with these slack variables? Right, the only difference is in the constraint of the alphas. Is the only difference. Alpha is not just bounded by 0 now, it's bounded by C on the other end. So of course, points cannot have infinite force. A large C means no slack variables, right? Or very little slack variable. Because a large C allows strong forces. A small c does not allow strong forces, but because it allows slack. So slack is essentially a way to compensate for a strong force. Instead of having a strong force, the slack takes away that force.
Why do we have per variable slack?
Because every point, in theory, can be inside the margin. But I won't have slack if alpha is, so one observation here that must happen is if alpha is 0, that's irrelevant. And what's going to happen with the slack? Do I need slack for an irrelevant point? What if alpha it's somewhere between 0 and C? Then I'm on that W times X plus B times Y is plus 1, right? The constraint has to be satisfied, so in that case, also, I don't need the slack. If a point is exactly here on the margin, the slack is 0. We don't need an error for points that are on the two margins. Only when alpha is C, I have slack is bigger than 0, and then the point is inside the margin. This is a homework exercise for you guys to figure exact how this works between alpha and the slack variables. What's the, when alpha is 0, when is it between 0 and C, and when is it C, and when is it slack? So the slack variables don't change the equation too much. What they really change is that I need to do some sort of either good choice for C or play with different Cs to see which one is the one I want, hyperparameter tuning. And that will definitely allow me now to work with many data sets, because the slack variable will allow points to go inside the margin. I don't have to worry in the 60,000 images if they're separable or not. Even if they're non-separable, I'm going to allow for those zeta variables to be non-separable. That means jump over the line on the other side. The nice thing about it is that SVM controls internally, if you allow me a certain amount of slack total, which points should get it. Right? So as part of the optimization, we don't decide, we say this is how much slack you have total. The SVM decides, okay, this point is the one close and it needs slack. This one is far away, it doesn't need slack, so on and so forth. So we don't have to do this in advance. We just tell it, like with regularization, here's how much L1 or L2 penalty you have, and regression puts the coefficients, decides which ones are 0 and which ones are non-zero for you. Same thing happens here. So this, in many ways, it's a regularization term. So back to my one thought that I had. If I have the alphas and the zetas, now I have the b's, I have the w. How do I do predictions? Very easy, right? I do w x plus b. You give me a new data point x, I do w x plus b, and depending when that ends up, I predict plus or minus, right? Can I do prediction directly from the dual? So obviously with the primal, I have wx plus b. If somebody gives me a test point, I run this formula and I get plus or minus sides. How far I go away from the line, it's my confidence that I'm on the right side. Can I do predictions from this? If I don't have w's and b's, just alphas, can I run the prediction from this formula?
Because for that it will be y.
Right, for this form in here, but if I wouldn't have the w, just alphas, can I write the prediction in terms of alpha alone? Not w, not b. That's a question I have for next time, if that's possible. Let me see if I can connect. I just want to show you one picture. Document is online. This is about the Karush-Kontaker theorem. The important stuff about this theorem and how it gets to the saddle point. This is my Lagrangian. There is no b in there. B is kind of included with the w's. So there's the w, which are the parameters, and the alphas, which are, this is the dual variables. These are the primal variables, right? And the way you think about it, when you take differentials, you create this, the objective function plus you add alpha for each constraint. That's exactly what we did. We take the objective, we added alpha for each constraint. And then the theorem, after some derivations here, the reason you get a saddle point is this is the saddle point. This is saying the best W and alpha combination correspond to this saddle point. If you keep W fixed, any way you move alpha, you get a lower value. AKA on the saddle, you get this way or that way, in a lower bound. This one saying, if you keep alpha fixed, any way you move the W, you're gonna go up from the saddle point. So this is saying that the best way for alpha is the maximum way you can, if you want to maximize this in terms of alpha, which is our dual problem, the maximum is in the saddle point. If you want to minimize this as a function of W, which is our primal problem, because we want to minimize the function of W, then the minimum is the saddle point. So the saddle point is the same. Either you maximize the dual or minimize the primal is the saddle point. And the picture I wanted to show you is this saddle. I hope it's this one. Not this saddle, there was a different one. I know where that is. There was a saddle with some equations on it. Let's say this one. The people who want to understand the mathematics of this can take some of the functions, trivial examples, some of them we did last time in class, and plot the saddle for those simple functions. Again, the primal problem is the problem that goes this way on the saddle, and it has a minimum. And the dual problem is the problem that goes this way on the saddle, and that has a maximum. And the 2 points are exactly the same point. The one picture that somebody asked me, and I wanted to show it here. So here's how to choose alpha and alpha j. You guys are gonna have a lot of fun with that, I'm sure. Coordinate ascent. This is the picture. I think somebody asked the question. Even if the data is separable, which line in here is better? Now, this line gets everything right. Right, the straight line. So that's more correct as accuracy. But this line looks more like in the middle, even though it gets this point wrong. So the moral of the story here, it's better to allow the slack variables and get the dotted line, because it's more bigger margins in the middle, even though it makes one error, so it needs to compensate this with slack here, than to force this line, which notice how close it passes to some points. That will be a very small margin to the support vectors. I'll be at office hours today, and hopefully soon we're moving to this homework, right? Homework 7.
मेरा ही नहीं हो रहा है अभी तक मैं 20 से मैं 30 पे आया हूँ
Did you keep